Hello, everyone, and thank you for joining us today for another Guideline Geo webinar. Today, we're going to be looking at the ABEM GroundTEM i5 and i10, the latest products in Guideline Geo's lineup of geophysical instruments. So my name is Jimmy Adcock. I'm the product manager for ABEM at Guideline Geo. I look after the resistivity, TEM, and seismic products. If any of you are joining us for the first time in one of these webinars, give you a little bit of background about the company. We are a manufacturer of geophysical solutions, manufacturing GPR, resistivity, seismic, and TEM instruments under the Marlow and ABEM brands. And the company has a reasonable heritage behind it, with ABEM having been founded in 1923. We have staff right the way across the globe. That's no exaggeration to say that. The orange dots represent where we have staff positioned around the world. And around that, we have our fantastic network of distributors who cover the rest of the globe for us. So that's a little bit about the company, but let's dive into what we're really here for, and let's talk about the new ABEM GroundTEM i5 and i10 instruments. These were launched at the end of February, so still pretty new, and we thought it would be useful to provide a public webinar so you could learn a little bit more about them. So our new TEM lineup looks like this now. We start with the GroundTEM i5. This is what we would call a true entry-level TEM system. We used to say that the entry specification of the WalkTEM 2 was an entry-level system, but let's be frank about it, it was still quite an expensive way to get into TEM, and we were looking for a way to help people onto the ladder and give people great TEM functionality without the same level of investment. Now, just because it's an entry-level system, don't confuse that with it being a basic system. This is a very competent TEM instrument, and the only thing that is limited on it is the output current, which is limited to 5 amps. So this is very much like the ethos of our Terameter VES instrument. Again, it's an entry-level product, but it is far from a basic product. Then we have the GroundTEM i10. Exactly the same instrument, same hardware, same functionality. The only difference is that we double the output current. And as we'll look at in a moment, when you're doing a TEM survey, one of the easiest ways to go deeper is to just apply more current to your transmitter loop. And therefore you generate a larger primary signal that allows the transient that we're mapping to travel deeper into the ground. So the i10 allows us to stretch the depth that we can get to. And these two instruments sit very well with our existing lineup of WalkTEM products. There's a bit of overlap between the i10 and the sort of bottom end of the WalkTEM 2 range in terms of depth capability. But then obviously we can stretch even further as we move up through the more powerful transmitters to the 20 amp transmitter and on up to the 60 amp TX60, which allows us to go very deep indeed with our TEM measurement. So let's have a look in more detail at the instrument itself. It's a self-contained unit. It's a single box solution with the transmitter and the receiver in a single rugged instrument case. You'll see it's bright orange, so it's an ABEM product, and we've got the name on the front there, the GroundTEM. And then on the back, we have a large cooling plate, which keeps all the electronics nice and stable during the measurement cycles. On here, we have some other decals, and most of these are there to act as guidance where you need it most, right on the instrument in front of you. And as a departure from our current lineup of ABEM products, this instrument is entirely controlled from a mobile device. And that can be a mobile phone or a tablet. It doesn't really matter. And it's designed to run on very low power basic devices. There is no great need for any powerful processing in the phone itself. The majority of that is being done within the instrument. And so therefore you don't need to also invest in the latest Samsung or iPhone to be able to run the instrument. It should run on pretty much any mobile device. If we have a look at in more detail at some of the decals around the box, as I said, they're there to give us guidance when we're setting the instrument up. So on the back of the instrument in the center here, we pretty much have all the instructions you need to undertake a TEM measurement with this device. So very, very simple process, and we'll look at the workflow towards the end of this presentation. We also have a generic sort of diagram of how it is laid out in the field. And then those are repeated on the ends of the instrument where you would connect the transmitter loop and the receiver coil. For the transmitter loop, we've also given a bit of extra information about the buffers that you might want to put between your measurement location and the nearest infrastructure. So what we see a lot in our support emails are issues with data quality, where the problem has been that the instrument has been too close to some form of infrastructure, either some utilities or buildings or some kind of other metallic structures that are creating noise within the data. So we've just got a simple infographic there to say you should keep at least twice the loop side away from the nearest piece of infrastructure. On the receiver side, because we've got a more complex connector, a multi-pin connector on the receiver side, we put a little reminder in there just to always check the connectors are clean and dry before you plug them in. There's also additional guidance in the app, and we'll talk about that as well towards the end of this presentation when we look at that live. There's nothing really inside the box that you need whilst in the field other than the 2 batteries that are running the instrument. So we have lithium-ion batteries, which are flight safe. You just need to pop them out of the instrument and put them in your hand luggage. And these are the only power that the instrument needs. There is no external battery on this, as there is with the WalkTEM 2. All of the power for the system comes from this. Receiver circuits and transmitter circuits, like in the WalkTEM, are completely separated, so they have separate batteries. So the RX battery is only powering the receiver circuits, nothing else. The transmitter battery is running the transmitter, quite obviously, and also the internal computer unit. So all of that is on one side, and then the clean side of the instrument is just the receiver circuits. That obviously means that this one battery is going to run down much more quickly because the transmitter has a much higher power budget than the receiver. So in the app, when the transmitter battery starts to get a bit low, it'll tell you and it will suggest that you swap the batteries over because the receiver battery won't have done much work at that stage, and then you can continue for the rest of the day. So we say that a single set of batteries will probably be good for something like 15 soundings, and that'll probably be a good day's work. Additionally, inside here, we've got some extra information just to remind you that if you have opened the box just before you start survey, maybe to put the batteries in, you've forgotten to put them in before you left the office, just a reminder to then pick the instrument up and put it upright. The reason why we want it upright is that the inbuilt GPS antenna that will give us positioning for every sounding is on the top of the box. So you'll get the best reading with that uppermost. And also, as we saw in the previous slide, the cooling plate is on the back of the box. So you want that to be able to get air blowing across it to keep those electronics nice and stable. The system comes with a bespoke battery charger. So this has 2 ports to put both the batteries in, and then basic instructions on how to check whether the batteries are charging and what state of charge they're at during the recharging cycle. This battery charger doesn't have an external adapter. You just have what I would call the Mickey Mouse connector on it. So that means that there's no risk of you kind of forgetting to take an external adapter. Now, I've done that with my laptop on enough occasions to know how frustrating that is. But with this, even if you forgot this cable, it's a very easy, very common cable to get hold of. And you just plug that into the side of the charger unit and you're good to go again. So it occurred to me that we might have some people who have signed up to this webinar who maybe are quite new to TEM as a method, not just to the GroundTEM instrument. So I'm going to run through a few quick slides about how TEM works and why it's a very advantageous way to measure the resistivity of the ground beneath us. For those who are familiar with TEM, you can sit back and enjoy your coffee for a couple of minutes. TEM is, as it says here, a non-destructive tool. We don't push any electrodes into the ground. It's an inductive method. So we have a transmitter loop that's laid out on the surface that generates the signals beneath it in the ground without a physical connection required. Unlike a VES survey or an ERT survey, electrical resistivity survey, where we have to hammer electrodes in, with this, we just lay the loop at the surface, and then we have a receiver coil at the center that is picking up the signals that come back from the ground. That means it's relatively quick to lay out. The measurement cycles are also pretty quick. We're talking about anything between sort of 2 and 15 minutes to undertake a cycle of measurement at one location. So if you compare that to doing a VES survey, where you need to constantly move electrodes further and further apart to get deeper and deeper, it's a very efficient means of collecting resistivity soundings. So productivity is where TEM really stretches its legs, as well as its ability to map conductive bodies very well. So when you're collecting 1D data, i.e. we are just getting a model of resistivity against depth, there are quite a few limitations in that method and assumptions that we have to make about what's happening in the subsurface around us. So if we can do more 1D soundings in a given time frame, we will have a better picture of what is really happening with the geology and hydrology beneath our feet. All TEM systems primarily consist of some way of transmitting, some way of receiving, and an instrument to record the signals. So with the center loop configuration that we use on the WalkTEM 2 and on the GroundTEM, we have a transmitter loop around the outside, receiver coil at the center, and then the instrument that is generating a signal to go around the transmitter loop and recording the responses that come back through that receiver coil. What we do with the system is we run current into the transmitter loop. So we switch current on and wait for it to stabilize, and then we leave it in that stable state for a short period of time. Physics textbooks will tell us a wire carrying a current will generate a magnetic field around it. So that's what we're trying to represent here. Red is the transmitter loop carrying the constant current, and yellow is the magnetic field that has been generated around it. We then switch the current off incredibly quickly, and what happens is that magnetic field collapses, and as it's collapsing, it generates eddy currents directly beneath the transmitter loop, and these eddy currents spread out and downwards, and we always say a bit like smoke rings into the ground. And because they are a flow of current, they are also generating magnetic fields, and it is those magnetic fields that our receiver coil back at the surface is picking up. Now, as the eddy currents, the transient, gets deeper into the ground, the secondary field becomes weaker, and it is that decay that we map. And the way that it decays tells us then something about the conductivity, the resistivity of the ground beneath us. So we take that decay curve and we can convert that into an apparent resistivity curve. So we have apparent resistivity on the y-axis and time after switch off along the x-axis. We then take that raw data, put it into inversion software, and the inversion software will generate or try to generate a model of resistivity against depth that would produce the same raw data if we repeated the survey over that model. Once we've got that model, then we can make our interpretation, and our interpretation could be absolute. So we identify a resistivity value and we assign some kind of material interpretation to it based on that value, or it could be a relative interpretation. So we look for where the resistivity drops in a given geological unit, and we use that as an indicator of the presence of water. And then we might look for where the resistivity drops again as an indicator of perhaps that water becoming less fresh and more saline. We can fine-tune the system by changing the configuration to either be better at mapping stuff that is near the surface or to be able to reach greater depths. If we use a larger transmitter loop, we will generate a bigger initial pulse, a bigger primary signal. And if we have a bigger primary signal for a given geology, that transient, those eddy currents should travel further into the ground before we lose them into the environmental noise that is all around us. With the receiver coils, if we have a very small coil, it will respond very quickly to fast changing signals, but it will lose its ability to record the signal much more quickly. Whereas a larger receiver coil will be able to scoop up more of that secondary signal and therefore have a better signal to noise ratio, be able to map that transient further into the ground, but it won't be able to respond to fast changes. Now, when we first generate those eddy currents, they are moving very, very quickly, and the secondary field is changing very, very quickly. And so therefore, we want a coil that can respond well. But at the same time, we want to be able to map it as deeply as we can. So there is always a compromise, and that's nothing new in geophysics. Pretty much every geophysical method has some kind of compromise associated with it. Normally it is to do with, do I want resolution or do I want depth? Now, the other thing that we can do, and we talked about this as being the difference between the GroundTEM i5 and the i10, is we can put a different amount of current into the loop. More current will allow us to create a bigger primary signal and therefore allow those transients to move further into the ground before we lose them into the noise. But that does come with one unfortunate side effect, and that is to do with how quickly we can begin a measurement after we switch the current off. So ideally, we would just pump as much current through the transmitter loop as we have available to us, and then start recording the secondary signals with a signal that is coming back from the ground. But we can't begin the recording process until all of the current has disappeared from the loop. So here's the current coming on, stabilizing, and then being switched off. If we put more current into the loop, it takes longer to get all of that current back out of the loop. And that means that we lose information about the near surface because that transient has already traversed part of the subsurface before we begin to measure the decay. So the obvious answer is, well, use a lower current, and then you'll be able to remove it from the loop quicker and start recording sooner. But then we have the problem that we are losing that secondary signal, that transient, into the background noise much more quickly. So that's where the concept of dual moment comes in. Dual moment means that we are putting in both high current and low current pulses into the loop and recording those together to basically create one data file, which uses the low current, the low moment for the near surface detail, and the high current, high moment measurement for the data from depth. And then we just end up with a single data file at the end that we can take forward for the inversion. So the instrument will pulse a series of low current, low moment pulses through the transmitter loop and then record in the off times. Then it will do the same with high current pulses and record in the off times pair. So dual moment is a feature that we have on all of the WalkTEM instruments and also the two GroundTEM instruments. So you get kind of the best of both worlds. So that's theory over and done with, and we'll move back to looking at the GroundTEM i5 and i10 instruments. So the i series, it's a user-friendly, app-controlled instrument. It's a one-box solution, and it's particularly lightweight. So the instrument itself, even with the batteries in, weighs only about 6 kilos. This allows us to undertake TEM surveys that are more affordable. This is at a lower price point than the WalkTEM 2. Less complex. The app is very simple to use, and you'll see that towards the end of the presentation when I give you a run through of how we would do a measurement, and also very quick to deploy. It's very easy to get this equipment into the field. So trying to make TEM more affordable, less complex, and quicker to deploy. As we said, we have the i5, which really is only entry level in terms of its investment costs and the fact that it's only a 5 amp output. And then we move up to the i10 with more current, and then we can get into the WalkTEM 2 range. These are some of the technical specifications for the GroundTEM units. You can find an expanded version of this on our website. Key things to remember from here is that it is app controlled. There is no external lead acid battery or lithium ion battery to carry into the field. It's just the two small batteries that go inside the unit itself. It's pretty compact, and we have the onboard GNSS to give us a global position for every sounding that we take. The system is single channel, so we can only have one receiver coil on it at a time, whereas with the WalkTEM 2, we can have two coils at once. And at the moment, there is just a single choice for that receiver coil. It's a flexible 3x3 meter 4-turn receiver coil. In terms of output, well, we've already talked about that. They're both dual moment, so they have a 1 amp output and then either 5 or 10, depending on the model. And transmitter loop options, there is a 20x20 meter loop and a 40x40 meter loop. Now, unfortunately, these are not the same loops that we would use with the WalkTEM 2. They are not interchangeable because the setup of the GroundTEM, the transmitter and receiver design is different from the WalkTEM 2, and therefore the design of these loops is slightly different as well. The whole system comes in a single rugged shipping case: transmitter loop, receiver coils, battery charger, batteries, and instrument. And when packed, that weighs about 30 kilos, even with the 40x40 loop in. So you can actually just stick that in a hold on a regular flight, just pay your kind of excess weight charges. So it is, again, very easy to transport this system. We'll have a look now at the individual components that make up a system, and then also the accessories that we can pair with the system if we were to acquire one. As we said, center configuration systems are made up of 3 components: an instrument, transmitter loop, receiver coil. We then have the transport case, and inside that transport case, we can fit the TX loop, the RX coil, plus the lead-in, the instrument, and the battery charger. And if we were shipping this on an airplane with us, we would be taking the batteries and sticking those in our hand luggage. So that's the entire system in one big box. The only other thing that we would also require is some kind of processing software in order for us to be able to go from that raw data to the resistivity model, the bit that gives us the value. And we would normally recommend to use Aarhus Sphere TEM and optionally Aarhus Workbench, but we'll look in more detail at those a little bit later. Everything in the orange box is included in the price of the system. So it's one price for the i5 and one price for the i10, and that includes receiver coils, transmitter loops, instruments, charger, batteries, and the big transport case. So if you were to come to buy a GroundTEM, your first choice to make is, do you want the 5 amp or the 10 amp instrument? And that would be based on either the depth that you need to get to, or primarily the depth that you need to get to, but it may be that you want to split the investment in your GroundTEM instrument over time. So you could start with the i5 if it provided great enough depth for your immediate requirements, and then at a later date, you could upgrade to the i10. We can do upgrades remotely from i5 to i10 in the same way that we can do remote upgrades on the WalkTEM 2 and the Terameter LS2. No need for the instrument to be shipped back to us. We can just update the license that's on the instrument, and you would then have access to the 10 amp output. So first would be the choice of instrument. There is at present only one receiver coil, so that's an easy choice to make. And then you can choose whether you want the 20x20 or the 40x40 transmitter loop. Obviously, the 20x20 is that little bit more portable, whereas the 40x40 gives us that little bit of extra depth capability. 20x20 arguably gives you a little bit better resolution of the near surface. Once you've defined your system that you're purchasing, then you have the choice of some accessories. So you could add the other loop. either the 20 by 20 or the 40 by 40 to give you more options, more flexibility. A spare set of batteries for the instrument is always a good idea. Although we said that that pair of batteries should be good for about a day's work, we know that sometimes it can be difficult to be able to recharge batteries when you're in the field, so a second set might be useful. And we also know that lithium-ion batteries in cold weather have a reduced capacity. So again, perhaps having a second set of batteries would be a wise investment. We also have in the pipeline the option of a profiling set of antennas. So this is a 3x3 transmitter coil and a 3x3 receiver coil that are semi-rigid with handles at the top, and the idea being that two people could then move this in tandem across the landscape, place it down, start the measurement, take a sounding and pick the whole lot up and move to the next location. And it would be far more efficient than laying out a loop at each location, each sounding position. You'd pick it up and move it along and should be able to achieve kilometers of survey a day. And this would also allow you to do profiling in a region where perhaps a towed TEM system just wouldn't be viable. So that's coming later in the year, so keep your eyes out for a news release about that. Software options for the system. Well, the first one's pretty obvious. That is the controller app, the GroundTEM app. This is for setting up the instrument and initiating measurements, and we'll have a look at this in a short while. At present, it's available on our website for download. It will be available in the Play Store in the future, as well as the iOS version, which is also following. It's very easy to use. You start the instrument has a Wi-Fi hotspot within it. You connect your device to that Wi-Fi hotspot. You then choose the script, and the script is really just based on the loop size that you're using, and then define how long you want to run the measurement for. And so there's no kind of having to choose how many times it stacks. Just say how long do you want the instrument to run for, and press play, and off it goes. And if you decide that you want to stop the measurement earlier because the data are coming in very nice and clean, like this example here, then you can press stop at any time, and that data file will then be closed off and saved at that point. You don't need to sit there for the entire duration that you've chosen. It also allows the option for adding field notes, or if there is anything unusual about the site that you're working on, or you see something in the data that you want to have a closer look at later, you can put a quick note into the app, and that will be stored in the project folder. Then we have the post-processing software, and obviously these are not included in the price of the system, so you can choose any post-processing software you wish, but we would normally recommend using Aarhus Spear TEM to generate the 1D models. So go from our raw decay curves to a usable resistivity model. It's a very easy to use package, and it allows us to output images of the models, images of the raw data, the model curves. It also allows us to very easily make one-page PDF reports that just have the model, the decay, the raw data and the model curve, header information about the measurement, plus tabulated set of results for that resistivity model. We can also export that table in an Excel CSV type format if we want to import it into something else. Optionally, we might want to add Workbench. Workbench allows us then to take those individual 1D models and do a bit more with them. We can combine them with base mapping. We can combine them with other geophysical data plots. We can also generate either 2D profiles through a series of 1D soundings, or a 3D block of resistivity data that we can then cut in any orientation. And as we see here, there's a sort of resistivity slice generated at a given depth, showing the resistivity variation across the landscape. So very powerful add-on to the Spear TEM software. But how do we make sure that we're getting the right TEM system for our requirements? Well, we now have this larger lineup. In summary, the GroundTEM is the affordable TEM solution in our lineup. If budgets are limited, or if you're new to TEM and you don't want to initially invest in sort of a full-blown walk TEM 2, then the GroundTEM is a very good choice and provides good surveys to depths of beyond 200 meters. It is the most portable system that we offer. So if you are having to do surveys in regions where it's important to be able to get in and out very quickly, or areas that are particularly inaccessible, like dense jungle or high plateaus where the climb up might be quite difficult, then the GroundTEM is a good choice. So we have our picture of our intrepid explorer here. In that picture, I have everything I need to do a 20 by 20 TEM measurement with the GroundTEM. So that's the 20 by 20 transmitter loop in my hand. And then in the bag, I have the instrument, the batteries, the receiver coil, and the lead-in for the receiver. So very easy to get into the field with this system. It's also very simple to use, and as I said before, we always prided ourselves on the fact that the Walk TEM and the Walk TEM 2 were pretty easy TEM systems to learn to use. You could train someone to go out and actually collect data pretty quickly on those systems. They're not particularly overwhelming in the way that they're set up. Nice workflow, but the GroundTEM takes this another step into an even easier way to deploy these systems and be able to collect that good quality data. You know, there really shouldn't be a barrier to you being able to send people out and come home with good quality usable TEM data. If, however, you think that your requirements might change in the future, maybe you might get involved with survey that requires either greater depth or a wider range of loops, then the Walk TEM 2 is a good choice. You can expand the receiver from the standard to the advanced. It gives you things like onboard processing. It gives you the Rakovsky coil for testing different damping resistors. It also allows you to run with the full suite of transmitters from the 8 to the 20 to the 60 amp versions, and all of the different transmitter loop and receiver coils. And that mixture of transmitters, receiver coils, and transmitter loops gives you a lot of flexibility in terms of how the system can be set up for a particular project. Obviously, with the larger transmitters, that enables us to go much deeper than we'd be able to with the regular GroundTEM systems. And at present, we have the ability to do the onboard processing with the Walk TEM 2 advanced models. So once we've collected data, we can run an inversion whilst we're still in the field and be pretty certain that we're going to take home data that when we do our full processing in the SPEAR TEM software, that we're going to have usable data and a good result. No nasty surprises. So to kind of round off the look at the instrument, before we move on to having a quick look at a data example, I'll just quickly run through the survey procedure with a GroundTEM instrument. So here's our intrepid explorer again on his way out to the field with the hardware. And the first thing that we're going to do is we're going to lay out our transmitter loop. So the transmitter loop is just a single length of wire, and a little bit different from the Walk TEM 2, it has the lead-in cable built into it. So the lead-in is a short length of cable that allows us to remove the transmitter and receiver some distance away so the loops can be offset slightly. And so with this, it's all in a single run. So we have double markers to show us when we get to the first corner of our square. So we would leave one connector by the instrument, pull the cable out until we get to a double marker, and then just peg that plastic peg as our first corner. We then run around the square, and it doesn't matter which way we go. The transmitter loop is completely reversible. We can plug it in either way round. We run around the square until we get to the next marker, turn through 90 degrees, and then we run to the next marker, and then back to the start. And when we get to the last double marker, that is the point at which we've started, and we then have the lead out back to the instrument. It isn't necessary to get these perfectly square when you're in the field. It will impact slightly the end model that we get if this is a bit more oblong or a bit more rectangular than it is square. But with these central loop configurations, it's pretty robust. You're not going to end up with something that is markedly wrong if this isn't a perfect square. Once we've laid out the transmitter loop, then the next thing we need to do is put the receiver coil in the center. But how do we know where the center is? Well, we take the lead-in part of the receiver coil and lay the end of that leading cable by the instrument and unreel it until we get to a double marker. So you'll start to see now why there's a mixture of double markers and single markers on the transmitter loop. Hold that first double marker on the lead-in where we have the double markers on the transmitter loop, and then we walk towards the location of the other double marker. So we keep all the double markers together. When we get to the end of the lead-in cable, we will then be in the right position to lay out the receiver coil. So the lead-in is specific to the size of the transmitter loop. There is a lead-in for the 20 by 20 and there's a lead-in for the 40 by 40. So once we've got that lead-in in place, then it's very easy to lay out our 3 by 3 flexible, and that has double markers on the corners again, so we know where to pull out to create the square, and that just plugs straight in to the end of the lead-in. And then that is our layout done. So all that's required then is to put the instrument at the corner, plug the transmitter in, transmitter loop in, plug the receiver coil in, switch the instrument on, and then we can move over to the app. So I will try and show the app in real time. So hopefully on here, I have a screen share of my mobile phone. So here on the phone is the GroundTEM app down at the bottom there. You would connect your phone's Wi-Fi connection to the hotspot on the GroundTEM, start the app, and at the moment it's giving me some advice because it's saying it can't find the GroundTEM instrument. So it's saying check that it's on, make sure you're connected to the right Wi-Fi network, turn off the internet data on your phone in case that's trying to take charge, and then make sure that the IP address is correct in the settings. So we can take that value and we can put that into the settings on the app. Now this is the regular production instrument IP address. It's the same for all of them, but I'm actually using a simulator because I'm not outside. So I will just put in a different address, which is the address of my simulator on the PC. Come back out, and then I'll just refresh the screen and we should connect through. So when we're connected to the instrument, this is what we'll see on the screen. And to begin a measurement, all we would need to do is select a protocol. And if we forget to do that and try and start the measurement, it'll tell us that we need to do that. And in here on a regular instrument, it would give us a choice of 20 by 20 or 40 by 40 meter measurement. In here, I have a protocol for the simulator. Then we assign the project a name. So we will call this demo, save. And then we have both survey lines and station numbers. So stations are the individual soundings, and we can tell the software that we are aligning those in a single line, and then we can add a second survey line or a third survey line, just to help us manage our data sets as we're collecting them in the field. Then we choose how long we want the measurement to take. So I'll just say 1 minute for now, just in the interests of speed. And all we need to do is press play. Then what we see at the bottom is the status of the instrument. So it is telling us that it has a lock. So we've got a GPS position for the sounding. It'll tell us how hot it is inside the box, so we can monitor that to make sure nothing is getting too high, too close to the red. And then we can see what the low moment and the high moment output is by the arrows here. And they should always be in that green sweet spot. So the GroundTEM will monitor the output current, and it will try and keep it constant to around 1 amp for the low moment and around either 5 or 10 amps for the high moment, depending upon which instrument we're using. That means that if the ambient temperature is different and therefore the resistance of the loop is different, or as the instrument warms up, the current that's being put through the loop won't change during the measurement. It should always be pretty close. Then we have the data coming in. So here are our decay curves, and you can see that every time it's done a cycle of low moment or high moment measurements, it refreshes these curves. So our low moment is on the left, our high moment is on the right. So slightly greater signal strength in the high moment. And we can see that towards the end of the decay curves, as the signal drops into the noise floor, that we see it starting to jitter. But what we would be looking for normally is that these curves are nice and smooth, and that would indicate that we're collecting pretty good data. The final tab we have gives us what I call the nerd box. There's additional information in here about temperature of the different elements of the instrument, the output, the exact output currents for the low and high moment, the voltage that's left on both the transmitter and receiver batteries, and also our live GPS position. We also have a neat option to be able to define the loop orientation. So our instrument is in the corner, and that's where the GPS signal is being collected from. But we can tell the system where the center of the loop is. And just to make it easier for you, if you press the help button, it gives you a quick diagram to show what to do. So you stand by the instrument, point your mobile device towards the center of the loop, and then press set. So as I turn my phone around, you should be able to see that the heading changes. And when I'm pointing towards the center of the loop, I just press set and it writes it in here. If my device doesn't have a compass, then I can press edit and I can type in a manual figure in there and enter that instead. Field notes can be added down here, as I say, if there's anything unusual about the site, and those will also be stored in the project folder. And that's pretty much it. That's one measurement done. We could now move on to our next station, define how long we want to measure for at that location, press play, and off we go again. So really simple to use, nothing really complex, no big complex settings to work through. The system has been designed to make a really straightforward workflow from setting that box down to having a box full of usable TEM soundings. Once we've collected our data, then we would want to get it off the instrument. So everything is stored on the GroundTEM in the orange box, not on the phone. One of the reasons for that is, again, so that you can use a very basic mobile device and not have to kind of buy brand new phones to be able to run the instrument. So we have the GroundTEM Connect software, which I should have opened before. Oh, help if I could spell GroundTEM. There we go. And this is just a very simple tool whereby we would now connect our PC to the GroundTEM Wi-Fi network. Here it is. And then once we're connected to the Wi-Fi network, we would just say connect to instrument. It would then, it won't do it now, but it would then read in the project folders that are on the machine. We select the ones that we want. We would say copy, and it would send those across to our local PC. You would have the project folder with the raw data, the field notes, all of that information in there, and then also USF file format of the soundings. So universal sounding format used by pretty much any 1D inversion software. So you can import that into your software of choice. So just to round off, I'm going to look at some data. And this data set was collected in Indonesia during a demonstration of the GroundTEM i10. It was part of a conference, and the problem with conferences is that conference hotels are rarely good locations to be able to do a TEM sounding. There is too much infrastructure. So we were very lucky that there was a beach right outside the conference location. So we took the loops out there and laid them at the top of the beach, sort of just above and into the high tide region of the beach. We were using the 20 by 20 transmitter loop. the regular 3x3 flexible receiver, and with it being an i10, we were alternating 1 and 10 amp low and high moment measurements during the cycle. Data have been processed in SPIA TEM. So here's a screen grab from SPIA TEM. It allows you to see where the sounding was taken. So that's being provided by the GNSS antenna on the box itself. And this is the raw decay curves. In green, we have the low moment. So the low moment is starting at the earlier times. That's the 1 amp measurement. And because it's 1 amp, it is the low moment. It starts to get jittery before the other part, the high moment. So we would remove those poor readings towards the end of the low moment measurements, and that's why those are in gray here. Then the high moment takes over and becomes the more reliable option, and that's in dark blue. And again, you can remove the data at the end where it starts to diverge and starts to fall into the background noise floor. We then take those active points, the ones which are colored, and we put those forward for inversion. And the inversion produced a model with a reasonable fit. The model fitted within the standard deviation of the data that we gave it. And what we could see was a shallow, higher resistivity zone dropping into something pretty low resistivity. Resistivity picked up a little bit and then dropped back down to a very low value again. And our DOI, our depth of investigation, was about 60 meters. Now, with the i10 and a 20-meter loop, you would expect to get considerably more than that, probably double that on a normal site, a more resistive site. But obviously, being a coastal beach, it's pretty conductive here. That it's salty sand falling into at least brackish and then saline water beneath. So this was the data that we produced during the demo, and we sat together and we had a look at it and tried to decide, hey, can we make an interpretation on this given where we've taken the sounding from? Now, we didn't really know what the geology of this particular region is, so we just kind of went for generic coastal model where you might be getting some saline intrusion under the landmass. And so this is a very generic kind of picture of what happens with fresh and salt water, fresh water on the land side, salt water on the sea side. And the salt water tends to push under the fresh water as it's denser. So could we use that very generic model of coastal hydrology to explain the resistivity values that we've seen? So if we zoom into that diagram to where we've got the beach, the fresh water and the salt water, the seawater, let's apply our resistivity model to that. So yeah, maybe we could. The high resistivity would probably be the relatively dry sand at the surface. It was very hot here, so even after the tide has been up and then retreated, the sand dries out pretty quickly. Then as we get deeper into the sand, it's starting to become saturated, and obviously the saturated the water that is causing the saturation is seawater, so the resistivity is going to drop considerably. And then potentially we're getting into a region where the fresh water from the land side is mixing with the seawater. It rained pretty heavily in the days and nights prior to this demo, so probably a reasonable amount of groundwater movement happening. And so that fresh, higher resistivity water mixing with the salt water pushes the resistivity up a little bit. And then when we get much deeper, well, then we're probably into the saline aquifer, into the pure salt water underneath. So this entire measurement, to go from laying out to collecting the sounding, that took about 15 minutes, then another 5 minutes just to pull everything in. And then it's a very quick process to transfer the data off the instrument and run it through SPIA TEM, and then be able to start making a first guess at why are we seeing the resistivity model that we do. So thank you very much for attending. I'm now going to have a quick look and see what we have in the way of questions. Is SPIA included, or do I need to buy it separately? No, you would buy that separately. It is an additional option. So some people may already have inversion software, so they may want to use that, or you can buy it at the time. But the package itself is just the hardware. And it's not, necessary that you have to have a WalkTem 2 or a GroundTEM. They sit together quite well in your geophysics storeroom, where when you're doing deeper surveys, bigger campaigns, maybe you want to use the WalkTem 2. But if you've got a small project where you just need to get out, get the data collected and get back, or as I say, it's an area where access is particularly difficult, then the GroundTEM might be the tool of choice. So perhaps you'd have both. And in that case, then you probably already got processing software, and it would just be the hardware that you need. I would like to just close by thanking you for attending, and I look forward hopefully to seeing you in another one of our webinars sometime soon. Thanks very much, everyone. Goodbye.